To do a video here on vector operations. In our previous video, we talked about what vectors were and how they compared to scalars, and we did a little bit of some operations with them. Talked a little bit how you arrange them to add them, the way you put them into a walkable path, something you can do like that. But now I want to talk a little bit more about that, go a little more in depth, and do a few more things that you really can do with this. So the first thing is components of vectors. Components of vectors. Basically, all the components really are is just the amount the vector points in each direction. Okay, so if I have some vector, let's say this is my vector, and I think I kept using A in the last video, so we'll use A. Here's my vector A. The components of this vector would be the amount that it goes, say, in the X direction, so I would just draw straight horizontal across until I got right underneath so that this is the same length, and then this would be, you could label it as the vector A sub X. That would be the X component of the vector, and then you can also have a Y component where you would just come straight up and it would be the length of it in the Y direction, and this could be A sub Y right there. And now the purpose of this is, what this basically does is it tells you if you traveled along A, how far would you have moved up, and if you traveled along A, how far would you have moved horizontally. It's kind of like if this was a map and up was north and to the right was east. AY would tell you how much you had moved away from the equator or closer to the North Pole, and this would tell you how far around the Earth you went just when you moved this way, because you went basically up and over. And if you remember back to our previous video where we were talking about adding vectors, if you look at the way I drew this, if I just walk along A sub X and then walk along A sub Y, that's basically how we would add any two vectors before, and that basically tells you then that A sub X plus A sub Y is equal to A. So if I add vector addition, if I do the vector sum of A sub X and A sub Y, these two component vectors, then I will get the actual original vector. So I could write something like vector A is equal to vector A sub X plus the vector A sub Y. Now I'm using the word component when I describe these. Technically, it's not really, the vector part of it isn't the component. The component would just be how long this was. It wouldn't actually be the vector part of it. But at this level, there's not usually a lot of distinction. There's not that clarification where when they say component, they just mean this vector here. Technically, the vector across here, A sub X, is the projection of it. And I mean projection like literally if we had a source of light right above this, A sub X would be like the projection of A on the ground. Like, so that was the ground. It would be like its shadow over here. So if we put the ground here and we had the sun at high noon shining straight down, A sub X would be the projection of A onto the ground, and it would be the length of that shadow, and it would be the vector. The length of that vector is technically a component, but we're not going to do a lot of differentiation there. We're pretty much just going to worry about component. This is the component, and this is a component. We're not going to worry about that, but sometimes it does help to differentiate between component and projection. And the same thing here. This is the vector is a projection, the length of the vector is the component. If I put like a big spotlight over here and there was a wall right here and we shine a light onto this arrow, then A sub Y would be the length of the shadow of it on the wall, and that would be the projection. It's kind of like if we projected a movie onto a movie screen. We projected it onto that screen, and that's where that term projection would come from. But for the most part, we're just going to talk components and not really spend any time worrying about differentiating between the two. But looking at this, components add up, they give you the vector, and then they also go ahead and create a nice right triangle. This also means that if I take the absolute value of each of these things, in other words, just the length of them, that I could write something along these lines. I could use this, the length or the magnitude of vector A squared is going to equal the length or the magnitude of A sub x, which is just that component length, plus the length of A sub y. And if you have this looking somewhat familiar to you, this is the very common Pythagorean theorem for right triangles. C squared equals A squared plus B squared. And that'll work here because this is essentially a right triangle, and we can do pretty much anything we could do with a right triangle with this, including doing the Pythagorean theorem, which I mentioned in the last video, I believe. And then we can also do, along with that, we can do some trig with this. We can do some sines and cosines. So in a normal right triangle, which I'll just redraw another one over here, we'll make it a right triangle, right? This would be our right triangle, and we would say that this could, let's say that this is our angle. We could look at this angle up here, but there's no real need to at the moment. This would be the hypotenuse. This would be the adjacent side. I'll put a P there, so why P? And this would be the opposite side from this angle. It's opposite, it's across from the angle, it's adjacent, it's next to it. So of the two legs of the triangle, it's either the adjacent side or the opposite side. If we did this angle up here, it would be 90 minus this theta, because there's 180 degrees in a triangle. That already takes up 90. This angle would be 90 minus whatever this one is, and then this would be the adjacent side to this angle up here, and this would be the opposite side from this angle. So you have to pay close attention to which angle you have. Always look at it, draw yourself a picture. Going across from it, that's the opposite side. Going right next to it, the angle is actually a part of it, drawn between it, that's the adjacent side. And then the side across from 90, the longest side, is the hypotenuse. Well, coming back over here to this picture, this would be the longest side. It's across from 90 degrees. So this would be our hypotenuse here. So this would be the hypotenuse, right? This would be the hypotenuse. This side here would be adjacent. So if this would be the angle here we're looking at to make it similar to this picture here. This would be the adjacent side. And this would be then the opposite side. It's opposite from it. And over here, we could define sines and cosines and tangent. And so cosine of our angle was simply the adjacent side divided by the hypotenuse. The length of the adjacent side divided by the hypotenuse. And then the sine of our angle was the opposite side over the hypotenuse. And then from there, we could define a tangent, which you could think of as simply the sine of our angle divided by the cosine of our angle. Well, the sine of the angle is the opposite over the hypotenuse, so opposite over hypotenuse. And the cosine is the adjacent over the hypotenuse. And if you rearrange this so that it's multiplication, you get opposite over hypotenuse from the numerator, and the denominator, to change the multiplication, you take the reciprocal of that. That's the hypotenuse over the adjacent side, and then the hypotenuse will cancel out. And all you're left with then for tangent is that it's the opposite over the adjacent side. Okay? And that would be tangent. I'll write that down here again just for some clarity. So this would be tangent, this would be cosine, this would be sine. And we can do a similar thing over here. We can say that the cosine of this angle is equal to the adjacent side, which is a sub x, over the length of the hypotenuse, a, not the whole vectors, just the length of them. And then the sine of the angle would be the opposite side, which is a sub y, right? Opposite from our angle there. a sub y over a, and then the tangent, and I won't go through the whole little derivation of that again, we'll just use this little version down here. It would be the opposite side, a sub y over a sub x. And we could basically use sines and cosines then to find any missing sides that we may want to. Or if we had all the sides, we could use it to find the missing angles just by doing what we used to do in trig class. So, for example, if let's say I was looking at this and I wanted to know what is the length of a sub x, right? What's the length of a sub x? If I have the length of this vector and I know what theta is, I know what angle it's at. Well, for that, I want to look at cosine because cosine has the a sub x length in it, and that's what I want to find. And then it also has the length of the vector and the angle of the vector. So it would be very simple, just one single line of algebra, just multiply both sides by the length of a, and I would then just get something like a sub x is equal to a times the cosine of that angle. And similarly, if I had the same information, I had the length of a, I had this vector a and its angle, and I wanted a sub y, I would just look to this equation here, multiply both sides by a so that a ends up over here in front of the sign, and I would get that the length of a sub y, the length of that is just the value of a times the sine of theta. So you can do little things like that. You can algebraically manipulate these and find these things. Okay, and so that helps you find the length of the sides. And so we looked at Pythagorean theorem. If you have the length of the legs, you do Pythagorean theorem to find the length of the hypotenuse. And if you have the length of the hypotenuse or the vector and the angles, then you can use sines and cosines to find the lengths of the legs. Now, what if you need to find the length of the angle? Well, you need the inverse operation for sines and cosines. And we discussed this a little bit in class, but we can go ahead and do that now. The inverse operation for cosine, like what do we have to operate on cosine with in order to get this cosine to be undone and get us this? And the answer to the inverse operation for cosine is the arc cosine. So if I take the arc cosine or inverse cosine, and remember this is not 1 over cosine despite this being to the negative 1 power, that just means it's the inverse operation of cosine, not the multiplicative inverse, not the reciprocal, not 1 over cosine. So be very careful about that. This is cosine to the negative 1 of cosine of theta, and then this would equal, if you took the arc cosine of one side, you'd have to take the arc cosine of the other side, and it would be a sub x over a sub y. And so what this says is cosine of theta tells you, or I'll point to this one, cosine of an angle tells you the ratio of the adjacent side to the hypotenuse, and the arc cosine of the ratio tells you the angle. So if I look right here, what's happening is I'm taking the cosine of the angle, so what's inside these parentheses here is essentially the ratio of the adjacent side over the hypotenuse, and then I'm taking the arc cosine of that ratio, and so that means that it basically, the arc cosine, if you want to say, cancels out with that cosine, but it basically undoes what the cosine does. It's a kind of equivalent to multiplying by 7 and dividing by 7. You ultimately end up doing nothing to it, so this left side would just be theta equals the arc cosine of a sub x over a. Okay, and that's pretty important, but it's not something you need to memorize. I mean, most of these aren't something you memorize. You need to know, of course, you need to have your sines and cosines memorized. You need to know these either in this form or over here in this form. You need to have those memorized, of course. You need to have your Pythagorean theorem memorized, whichever version of these helps you. You need to have that memorized, and of course that these add up like that. This is in the vector version. This is in the just links of it version for the Pythagorean theorem. You need to have that memorized. But this here you don't need to memorize because you can just do one little line of algebra and you get to this. And same thing here, you just take an arc cosine of both sides and you've gotten to this answer here. So these ones in the middle, I wouldn't spend any time memorizing. You just need to know how to actually come up with them real quick. So similarly to doing something like that, you can get theta from sine. So you could take the arc sine of both sides. I won't go through doing that, writing it all like I did for the cosine, but you get arc sine of a sub y over a. And again, just the lengths, I'm not putting any vector signs over that. And then the same thing with tangents. If you know the lengths of the two legs, then you can take the arc tangent or inverse tangent of both sides, get a sub y over a sub x. Okay, so at least just doing some basic trigonometry and some basic Pythagorean theorem lets you find the lengths of the missing sides or the angles or breaking it into components like we did, because essentially if you ever asked what is the x component of such and such vector and they told you the vector and they told you the angle, you would basically come right here, you would use the sines and cosines, or if they wanted the x component you do the cosine, multiply, write this out, multiply the length of the vector over here, and the only thing that would be left, you just want to isolate the a sub x, that component of it, and you would end up with this right here, and you would use that and you'd say, all right, the x component is this, and then similarly if you needed the y component, if they asked you for that, you would just do that again but with sine and get that the y component is that. It's something that you'll do so much that eventually you won't actually go through multiplying this over. You'll just know, oh, it's just this component is just a cosine theta, and this component is just a sine theta. It'll become very normal, and you'll get used to doing it. And then again, if they ask you for angles, you're going to have to use arc cosines and arc tangents. So these guys right here, again, you don't need to memorize those because you can just do just one line, do the inverse operation of cosine, inverse operation of sine, inverse operation of tangent, which is arc cosine, arc sine, arc tangent, or inverse cosine, inverse sine, inverse tangent, which is a little button on your calculator, and you just go through and you do it. Okay? And then beyond that, what if we're adding multiple vectors together? Well, the trick to that is to basically, if we're doing more than just two, if we're doing any two, we can just go ahead and make a single right triangle of it. But what do you do if there's 3 or 4 or 5? Well, the goal there is to make one big right triangle. So let's say I had this vector, and I'll call that A, and then I had another vector, let's call it B, and then I had a third vector that, say, pointed down like this, and maybe we'll make that one a little longer, vector C, and I say what is A plus B plus C? And the trick to this, if you draw it out, it becomes a lot easier to see. You're going to want to break these into their components and add them up through the components. And doing this, I'll sketch out why you would do this. You don't necessarily have to draw this out every time, but I'll sketch out why you would do this, because doing this allows you to make one big right triangle. So we'll draw it without doing that just first. You would come in and you would say, okay, the components here would be a sub x, and you'd use all those math equations we just did above, and you'd find a sub x and a sub y, and you'd find the length of both of those, a sub x, and you find those both lengths, and then you'd break b into components, okay, b sub y, b sub x, and you do the same thing for c. You'd use all that stuff we did before, and you would do, here would be c sub y and c sub x. Notice it doesn't, if you think back to our adding vectors, it doesn't matter which order. It doesn't matter if I do b sub x, b sub y, or b sub y, b sub x, and go across the top, because the order that you added vectors in didn't matter. So I can do the y one first here, just because I would have gone right over top of my my c label there. And so if you want to do the addition of these things, well, what you're going to want to do is add up all the x components and then add up all the y components. And when you do that, what's ultimately going to happen when you do a sub x plus b sub x plus c sub x, it's like you're taking all three of these. You're doing a sub x, b sub x, and then little c sub x. So you have a sub x, b sub x, c sub x, and of course these are still vectors. You have all of those together, and then you add up the vertical components. You'd go up a sub y, you'd go up b sub y, and then if you look at c sub y, I didn't put my arrow on it, it's pointed down. You'd come back down c sub y to there. So it'd be, a sub y, b sub y, and then c sub y would bring you back down to right here. I didn't put it right on top of those, I put it next to it because it would have gotten kind of messy. But when you do that, what you end up with is look at this, draw this in from, remember, when you want to complete this in, you draw from where you started to where you ended. And all of these are on a walkable path. I'd walk along A, then walk along B, walk along C, and I'm always going in the same direction as the arrow. I'd walk along A sub y, then walk along B sub y, and then I'd walk back down along C sub y. So it's like a path I followed. I just wandered over, up, and back down. And then this gives you an overall right triangle right here. Okay? That line got a little off. But this would be just a right triangle again. And we know how to solve right triangles. So if we wanted to find this resultant over here, this vector would be the vector A plus B plus C. And I just want to go ahead and call that the resultant so I don't have to keep writing that all out. So I'll put that over here. This is R. The resultant equals. All I would really have to do then is add these up for my x component, these up for my y component, and I've got it, which means all the x components added up, that's one of the legs of my triangle. All the y components added up, including this, which would be a negative number here because it's going down, a negative c sub y. Add up all the y components, and then I'll have this leg of the triangle, and I can solve for r by saying that the length of r, the magnitude of r squared, is going to equal the length of a sub x plus b sub x plus c sub x. Oop, that was supposed to be an x. It looks like a y. Squared. That would be that leg. And then the other leg would be a sub y plus b sub y plus c sub y squared. And remember, this c sub y in this case was negative because it's pointing down, but it doesn't have to be. It could have been positive. It could have taken it up higher, in which case our resultant would have been pointed somewhere up here or something like that. Or it could even be 0. This could have been just a vector pointed straight down, in which case there was no y, or I'm sorry, a vector pointed just straight horizontal, in which case there was no actual y component to it. That's possible as well. But basically just adding this up gives you one leg of the right triangle and then the second leg of the right triangle. Okay, and so this lets you add up a bunch of vectors that aren't at right angles to each other, and it'll get you the same answer. And you can also look here. A plus B plus C would be the same thing as C plus A plus B. So, and vice versa. You could flip these orders around in here, and it really wouldn't matter. The same thing here. You could have added these up in any order you wanted. You could have done B, then C, then long A, and you could have done negative C, and then back up A, and then back up B, and you could have just, and you know what I mean, could have gone down C, up A, up B, and you still would have ended up right here. It really doesn't even matter what order you add the components in, but it allows you to add up multiple vectors that aren't making right triangles, because if you just draw out A, B, C, you don't, oh, that's not a very good C. But if you draw out A, B, C, if you draw those out, they are definitely not, right? So this is vector A, vector B. They're definitely not making a right triangle. And your resultant would be right here, right there. This would be that resultant. It's definitely not some right triangle. That's a crazy shape, but by adding up the components, by breaking each of these into components and adding up the components, paying careful attention to any that might be negative, we were able to instead just turn this into a right triangle, which is easy to solve using Pythagorean theorem. And if you look here, the result I got here, even though it's not perfectly drawn straight, I mean, if you look, it's at about that same angle and same length as what I came up with here when I added up all the resultants. And if my handwriting was perfect and all my lines were perfect and at the right angles, these wouldn't just be about the same, they would be exactly the same. This resultant here would be the same length as this resultant here. And so that pretty much covers what you need to do as far as operations on vectors and how you go about adding them together. Also keep in mind, though, that once you have this into the form of a right triangle, and you've done this and you've got the two legs, you can still go back. You can also even find this angle that this would be at. It would be a lot easier to find this angle here, this angle theta in there, using a right triangle, than to try and draw out some horizontal line and figure out, well, what angle theta, whoa, that went crazy on me, what angle theta did this end up at? And it would be much easier to work with right triangles, so keep that in mind. Turn things into right triangles by adding up all the components. Make yourself one right triangle, one big right triangle, and just do it the right triangle way from what we learned above. All right, that's all for now.